Hello, everyone. This is Scott Lee, and today's date is March 11th, 2025. And in this presentation, I wanted to go over a very quick case study for a thermal expansion of a bar element. And what you see here is a figure of an actuator, just for illustration purposes. So the main intent of this example is to perform a case study of a bar with fixed boundary conditions under thermal loading. We want to study essentially what is the internal forces that get developed within the bar. And then in the second example, I wanted to add some compliant C pushes at the end of the bar to study the change in bar forces under thermal loading. So um, this slide here wants to go over some very basic mechanics of materials equations to determine the internal force within the bar. We don't need FEM, and in this video, I'm going to go over the model in Femap since I'm an avid Femap user. But in this idealized problem statement, you can determine the bar forces by simple mechanics of equations, mechanics of materials equations. So as you can see here, we have the stress equals E times epsilon, stress equals E times strain. And then when you decompose that, that's P over A equals E times epsilon. And for thermal analysis, we know that the strain of a material is equal to the alpha, which is the coefficient of linear thermal expansion, times the delta T. Delta T is the change in temperature. And then so when you decompose this equation, it basically comes out to be the internal force within the bar P is equal to E times A times alpha times delta T. And here are some of the inputs for going to be using some just arbitrary values. And so for this example, I'm using steel 29.0 E6, cross-sectional area 0.5 inches squared. The coefficient of thermal expansion is 6.6 e to the negative 6, and the delta T is 100 degrees Fahrenheit. So basically that delta T can be assumed as a starting initial temperature of 70 degrees Fahrenheit, and then you apply a hot thermal loading of 170 degrees Fahrenheit, so that difference would be 100 degrees. So we're going to be looking at a hot case, not a cold case. And so when you put that all into the equation, you get this value here, 9,570 pounds of internal force within the bar. And please note that the bar force is in compression. And we're going to go over why that is the case. So basically, the internal force is in a state of compression whenever there is a hot thermal load when you have fixed boundary conditions on both sides of the bar. This makes sense because the bar wants to expand due to a hot thermal load, but due to the fixed boundary conditions, the bar is essentially prevented from expanding, and therefore an internal compressive force will be developed within the bar. Another important thing to note based off these equations is that the internal axial force within the bar is not a function of the length of the bar. Nowhere here in these equations do you see the length. So that's just an FYI. So to kind of illustrate what what I was trying to say previously is imagine this orange square, a rectangle as the bar, and then the reds are assumed fixed boundary conditions, and then you apply a hot thermal loading. As I mentioned previously in the previous slide, the orange bar will want to expand for a hot thermal loading, right? But because the red rectangles are meant to represent fixed boundary conditions, essentially the bar is restrained from expansion, right? So if the bar wants to expand, the orange will want to move outward, left and right, right? But because it's prevented, there needs to be an internal compressive force to balance out that expansion due to the fact that we have applied these fixed boundary constraints. And that's what you see here is this orange is the arrow that is trying to illustrate how the body wants to move due to a hot thermal loading. But this red is the force that's being applied due to the fact that we have fixed boundary conditions. That's what this simple illustration is supposed to represent. So let me quickly go over the model that I have built with you guys. Here is a simple bar element. And as I mentioned in the previous slides, the material is steel, 29E6. Here's a coefficient of thermal expansion. The property of the bar, as I mentioned, is 0.5 inches squared. The loading will be a initial temperature of 70 degrees. And then the final temperature will be 170 degrees. So the delta T of 100. I have applied fixed boundary conditions on both sides of the bar. And when I run that, you will see that when we look at the internal forces within the bar, we get an internal force of 9,570 pounds in a state of compression throughout the entire bar elements, as you can see here. So this matches exactly with the this equation here. So that's good, right? That's what you want to see. Now let's move on to the second example. So in reality, a bar is never fully 100% fixed on both sides in a real world example, right? Like if we take a look at this actuator and it's being connected to some kind of structure on one side here, and it's also connected to another compliant structure here. It's not a fully fixed system, right? This fully fixity is just an idealization, and it's just to kind of give us a sense of what the numbers would be for this very conservative idealization. But in reality, as I mentioned, it typically the boundary conditions are compliant. So what if we were to take this example to the next step and actually add compliant springs? And so basically what I'm going to do is basically apply a spring C-bush here at this end, as well as a C-bush on this end. So let's take a quick look at that. So here are the C-bushes. I'll highlight them for you here. So you can see a C-bush here and a C-bush here. So I added another node because the C-bush needs two nodes, right? And then they're coincident, so I had to actually add a corner system. And this is the corner system here. Don't worry about the Y and Z's. I'm just trying to get the X vector that's aligned with parallel to the bar. And so when we look at the properties, I just came up with an idealized property. This is just for idealization purposes. But if I assume a stiffness in the X direction, which is along the axis of the bar at 90,000, that's just for idealization purposes. I did not calculate this from any kind of equation or anything like that. And I set everything else to a low value because I just want to have stiffness basically springs in parallel, right? And so if I did that, what do you think the internal force of the bar would be? So let's take a look. If you guys can recall springs in series, you guys will definitely recognize that the force in this bar relative to what we saw in the previous example for fixed, it definitely should be lower, but how much lower, right? And so in this particular example, when adding those springs on both sides, added a spring here, added a spring here, 90,000 pounds per inch, just an idealization. The internal force within the bar comes out to be 815 pounds. Okay. 850 pounds, as you guys can see here. Let me let me make that bigger so it's easier to see. Okay. So let's go back to the previous example. I calculated 9,570 pounds for a fully fixed system, and now we're seeing a 815 pounds of compressive force. So that's nearly an order of magnitude decrease in the bar forces. So why is that the case? Um, so determining bar forces with compliant springs at the ends of the bars, springs in series. For springs in series, the equivalent spring constant KEQ can be calculated using this following equation here. And K1, K2, K3 are the spring constants for the individual springs. So basically, we have in our example, second example, we have the C bush as a spring, the 30-inch bar, the bar element is 30 inches long, and that's a spring. And then we have another spring on the other side. So we have three springs in series, right? And then this is how you calculate your K equivalents. So knowing those values, let's try to calculate it by hand and then see if that matches with what we see in the FEM. Okay. So as I mentioned, the spring stiffness in the X direction is 90,000 pounds per inch. So let me show that one more time. So let's take a look at this spring here. Modify, edit, property. Modify, edit, property. This guy here. And you can see here it's 90,000 pounds per inch in the X direction. The stiffness of the 30-inch bar, basically this guy here, the bar element, this entire bar element, is calculated to be EA over L, right? So E times A over L, and then the L is 30 inches. That came out to be 483,000 pounds per inch. And so obviously the second C bush on the other side is the same in terms of the stiffness. And so when we calculate using this previous equation here, 1 over KEQ equals this value, and then when we take the inverse of that, KEQ is 41,000, around 41,000 pounds per inch. So essentially, what we're seeing is a significant decrease in the overall stiffness of the entire system when we add those compliant stiffnesses, springs, which makes sense, right? And when we take the ratio of this KEQ versus the stiffness of the bar, so 41,000, divide that by 483,000, that ratio is about 8%, 8.5%, 0.085. And then when we multiply that by the fixed bar forces that we were calculating in the first example of 9,570 pounds, we get around 815 pounds, which actually matches perfectly with what we see in the FEM. So what the FEM is showing us and our calculations are showing us are matching perfectly. And show that again here, 815 pounds throughout the entire bar. Oops. So in summary, an idealized fixed boundary condition leads to high development of bar forces. In the real world, this is not realistic and an overly conservative assumption. So definitely be careful if you ever do thermal analysis by assuming this artificially stiff boundary condition, which is not realistic. It does give you a kind of a rough idea. Very quick calculation will give you a rough idea of where you stand in terms of internal forces within the bar. But when you start adding the compliant stiffnesses, obviously it's going to reduce by possibly an order of magnitude, as you can see here. But it'll give you kind of a first order answer if you were curious. If your boss asked you like, "Hey, what is the internal force within this bar that's representing an actuator at your job?" Right? You can just do this quick calculation and be like, "Oh, I'm getting around 10,000 pounds, but this is assuming fixed boundary conditions, so it's too conservative." And when I start adding the compliances at the both ends, it should possibly reduce by an order of magnitude. Let me run the FEM and see. And yeah, so that's basically what I wanted to go over in this quick case study. I know this is very basic, but it's also very powerful by understanding some of these fundamental concepts. So thank you.